It's about declarative lifecycle management in digital twins. Eduard, the floor is yours.
Yes, thanks a lot. Yeah, so this is joint work with my colleagues from Oxford University and with Nelly Bencomo from Broch University. And I'm going to present some work on digital twins of self-adaptive systems and how we can use self-adaptation during the life cycle. So this is how we normally see a digital twin. We have on the one side the black robot arms, which are physical entities, and on the blue side we have our models, and somehow we send data around and we do commands. One view of this is that we already do self-adaptation, right? Whenever we see some behavior from the physical entity that we did not expect, then the digital twin is actually adapting with the commands. But one special thing about the digital twin is that because it's supposed to be there for the whole lifetime of the physical entity, we need to make sure that we have the right system, that we have loaded the right modules, that we have connected them the right way. If I have, for example, a robotic, if I have a part of my factory where I have some robots and I have 3 of them, I probably want to load 3 different models for them. And I want to connect them in a way that I can do the services that I want to provide to you. And they change all the time, right? Machines break, they go into maintenance, I replace them, requirements change, everything is changing. So I cannot rely on the fact that my system is a correct digital twin now at every point when these changes happen. So if we now go back from all this model view, at its core, every single model is a self-adaptive system. And what it's doing is performing the Medicaid framework, which is the framework which is common to self-adaptation. So you have a system split into 2 parts. You have the managed system, in our case the physical twin, and you have the managing system, which is the digital twin. And it performs 4 different things, which is I monitor what my managed system is doing, I analyze whether it's doing the right thing. If it's not doing the right thing, I have a set of actions that I can perform. I start a planning algorithm to get back to the behavior I want to have, and then I execute. And you can apply this directly to many digital twins, and you get self-adaptation of behavior. Now, as the physical entity is changing, as it goes through its different life cycles, we need to change the managing system as well. Because that I am using the right analyzer now does not mean that I use the right analyzer the next day. For example, if I analyze certain requirements on one of my robotic arms, or let's say I have a greenhouse in a smart manufacturing or smart agriculture setting, if something goes into maintenance, I need to monitor and analyze different properties. And what we do in this work is we look at exactly this question. So how do I self-adapt not the behavior of the physical twin, but the structure of the digital twin itself? And we end up with a 2-layer self-adaptation architecture, so we have another mechanism up front. And one key ingredient is that we define the life cycle in a declarative way, because we need this to enable generic planning. Let's look at what I mean by life cycle. We understand life cycle a bit more generic compared to manufacturing. We assume that each physical system has different stages, and in these different stages it has different behavior and different requirements. If we stick with our greenhouse and smart agriculture, we can have 2 stages. We have the left one, where the plant is healthy and happy, and you can have the right one, where it's unhappy and sick. And let's say I don't want to water a sick plant as much as a healthy one, because it's sensitive to moisture. Now I can, this is what I have already done here, can have a simple transition system. If I see that my plant gets sick, then do something and go into the other state of the transition system. That works as long as you have 2 life cycles, 2 stages. Because this plant alone, and I'm not even covering all the smart stuff around it, has different life cycles. For example, it's growing. And again, I can do the same thing. Well, I need probably to water a big plant more than a seedling, and I can do transitions and so on and so forth. And they all interact. And now I can do the cross product of all my transition systems, and now I need to be very, very careful whether the cross product makes sense. What is actually the action I want to do when I go from a happy seedling to an unhappy big plant? And then I have dozens of life cycles, and I have a big system with a lot of components, and they all do this. Do we really want to have the whole transition system? Do we really want to design it and find out what are the transitions and introduce modularity there? Probably not. It also vibes with the make K. Because remember, there was this planning stage where I see I'm in the wrong configuration, and now I have a set of actions that I want to perform to fix this. And what the transition system is actually doing is it fixes all plans, which means that you need to design all of them upfront. So we want to have a declarative view. We don't want to say, if you see that you're a big house plant with this action, we want to say, what does it mean to be in the life cycle stage? And what are the possible actions to get it? And then we are able to have our two-layered architecture, which is just putting a map cable on top. But note that this map cable, so the upper managing system, it is not managing behavior. It actually doesn't care that much what the physical twin is doing. It's monitoring structure. It is structural self-adaptation. It is not responsible to make sure that the physical twin is behaving correctly. It is making sure that the layer 1 architecture has the right means to react. So everything in the lower box becomes the management system, including the upper management system. And we monitor what are the components assigned to the physical twin, and how can I remove and head them. Right? And if you would have an operational view, I would need to have the planner by now ready. But we don't. Instead, each of our life cycle stages is defined with two predicates. The first predicate is, am I a member of this stage? Am I sick? Am I a seedling? Whatever plants can be otherwise. And the consistency predicate, which is, given that I'm a big plant, what are the analyzers, the monitors, the planners, and the executors in the layer 1 system that I need to have? And what we will do then is, well, I look at, am I a member of a stage? Am I consistent with the requirements? If not, what do I need to do to become consistent with it? The actions you have is adding and removing components. And as you will see in a moment, planning is just a touch. So a little bit more mass, there will not be a lot of mass, I promise. A stage is a tuple of two predicates. The first one is membership, the second one is consistency. And this is the definition of a life cycle stage for a sick plant. So we say that a plant is sick if it has an NDVI under 0.5. This is a measurement on how healthy a plant is, essentially. You can do this with infrared sensors. And I say, well, if it's sick, then I want to have an analyzer for it, which is for the moisture property, and it makes sure that moisture is below 5. That's it, right? No transitions whatsoever. This is the stage for a healthy plant, and a healthy plant is healthy if it's not sick, so the value is over 0.5, but I need a different analyzer. The analyzer makes sure that I water under the level of 10. Right, so healthy plants can be watered a little bit more. And if you're wondering about why do I have such a strict boundary, of course you can have a third stage where you are in an epsilon around 0.5 and both consistency predicate. So now a life cycle for us is a set of the stages with few conditions on it. The first condition is I'm always in one of them. And the second one is I'm always in exactly one of them. So no matter at what plant I look at, it is either sick or unsick. Which means that I don't fall out of my life cycle and I'm not in the situation where I'm in two stages at the same time. I need to more or less explicit. Note that we can define this very nice in a logical way, which means that if I have all my predicates, I can ask any SMP solver, is this a life cycle? If I am in a lot of life cycles and they don't interact with each other, the declarative phase also gives you a way to handle this. So the compatibility condition we have is that if an asset is in two life cycles, there must be a way to make it consistent with both of them, right? So if I have an A, and A is in D1 and D2, so it's a member of both, there must be a set X of components that make it consistent with both of them. Again, this is declarative. This is something I can ask an SMP solver upfront and ask for. So this makes two support if you would implement this fully person. This is of course the case where the life cycles don't interact. If they do interact, then I need to model this. And this is how the hosting works. We monitor both the physical twin and the layer 1 architecture. We have a knowledge base in the middle where we store what components do we have, what physical twin are they responsible for. Then I run my consistency queries, find out whether I'm inconsistent with something, and then I ask the planner, please give me a plan to repair it. And then we execute it and store the results in that knowledge base. Now planning, right? So I have said the planning can be done easily with logic, and indeed it can be. Because what we do is we do abduction. Abduction is, for those not that familiar with logic, I give you a set of formulas and I give you a fact that must be implied by that. For example, I want to imply that I'm consistent with a stage. If the set of formulas I give you does not imply the fact, I want to add additional formulas to my theory that explain my implication. And this is standard first order logic reasoning. Most SAP solvers can do this. I will come to an example in a moment. But how the second mapping works is as follows. We look at every asset, we look at all the assigned components to it, and then we try for every stage, am I a member of it, and am I not consistent with it? Because if I'm a member and I'm consistent, then everything's fine. If I'm not a member, then I don't care anymore. And then we ask, give me an explanation x prime, such that if x prime would be true, if this would be my components, then I would be consistent. And then planning or execution is, can I actually remove everything that is left over, and can I add all the components which I x prime and not? And if you do this for multiple life cycles, you just have a little bit more conditions. So let's have an example. Let's say my knowledge base has stored that P has a value of 0 or 4, so it's it. Sadly, my analyzer is still from my old stage, so it's for the healthy one, so I know that I'm a number of 6, but I'm not consistent with. And now I ask, what formulas or what facts do I need to add such that I am a member of consistency? We give this to a logical solver, and it will tell you, well, if you add this fact here, then P would be inconsistency. That's great. And then we just add this to our component. This corresponds exactly to adding a new analyzer component. If I'm a little bit more clever, I can also find out that I can remove the old one, and then I execute the plan instead of I add a new service or a new form. This is also very, very great for abduction, right? Because I do not ask for an arbitrary formula to explain my implication. I actually ask for a simple fact over a fixed signature. So this is very, very great for abduction. So what you need to implement this is you need some kind of data structure that allows reasoning. You need to be able to do deduction on it, because you need to find out whether the predicate holds. You need to be able to abuse over it for the planner. You need to represent structured data, and it would be great to query and have asset model information in it. And thank God people already do this, and this is exactly what a knowledge graph does. And the kind of abduction I described is a box abduction with a fixed signature, which is efficiently solvable and for which we have implementation. So we have implemented this for our small greenhouse in Oslo. So this is the camera which has an infrared component in it, which actually measures this weird index that I mentioned to you. And it fits perfectly. It is completely knowledge graph based, and we could just put our system on top without problems. There are some more details in the paper where we show that knowledge graph also scale very, very well, because you can build them all the time, all the information that they have. So to conclude, what were our main contributions? We were building on this perspective of digital twins as self-adaptive systems, and we all realized that they don't need to just adapt the behavior, they also need to adapt the structure. So we have introduced a declarative way of lifecycle modeling, which allows us to do abduction for planets, and we did a two-layer self-adaptation architecture, which builds on this declarative lifecycle management. For further work, it would be interesting to have more operation operators, so you have more conditions than just compatibility. And finally, now that we have one-layer architecture for behavior and two-layer architecture for structures, what's the general case, right? So if I have a changing mecha model, for example, do I have like the same layer on top to have 3 layers self-adaptive digital? But this is something that we would like to explore. How many layers can we have that actually still make sense and led to something? Thank you.
Thanks.